This is Lab 5, Frictional Force of an Inclined Plane by Carter Yunt. The objective was, using an object sliding down a surface at a constant velocity, find the coefficient of friction between the surface and the object. So givens our mass of the object is 0.093 kilograms, height of the slope is 0.0691 meters, and base length of the slope is 0.2962 meters. What I really did here was I took a notebook and I set it at an incline. And I took my mouse from my computer and set it on there and tried to find the angle at which it would slide down at a constant velocity. Once I found that incline, I let it go and used Tracker to model the data. So here's the Tracker video that I used to model that data. As you can see, the mouse really does not accelerate much. So we're going to talk about some of the physics concepts in this experiment. So we have the box sitting on the inclined plane at theta, as we define here. And we got normal force acting up here. Normal force we're going to set equal to the force of gravity acting down times cosine of theta. This theta is the same as this theta within this angle. And then we have the friction force acting to the left of the block up the plane equal to mu, the coefficient of friction, times the normal force acting up from the plane. We already found the normal force is equal to mg cosine theta. So we can set friction equal to mg sine theta, which is the only force acting down the plane. Those forces are the same because we have no acceleration. As according to Newton's second law, force is equal to mass times acceleration. Because there's no acceleration, there's no net force, which means the force of friction must be equal to the force of gravity acting down the plane. Alright, so to calculate theta, we took tan negative 1 of y over x. So theta equals tan negative 1 of 0.0961 over 0.2962, which is 17.97 degrees. These approximations were calculated using Tracker. So some calibration tapes were set at the height of the angle and the length of the angle to find this. So we have constant velocity, no net force. Normal force is the y component of gravitational force, as we talked about earlier. Frictional force is going to be equal to the x component of gravitational force we talked about earlier. So we talked about Newton's second law being equal to F net equals mass times acceleration. Since acceleration equals 0, F net equals 0, the force of friction must equal force of gravity acting along the plane. So some initial inputs in Python. What I did was I used Excel to import all my data from Python. I imported the time, the x, and the y from Python. And then I took the change in x, the delta x, and the delta y, and calculated their average, as you can see down here. And then took the velocity in x, which was the change in x over the change in time, which is always 0.02, because this was the time step set in Tracker, to calculate the overall change of velocity of x, as you can see here. I did the same with the y direction. Then I used these and imported them into Tracker itself. So you can see velocity is equal to negative 1.89090909 in the x direction, negative 0.04909909 in the y direction, and 0 in the z direction. The delta t I set equal to 0.02, which is the same time step for Tracker, and mu I actually calculated outside of Python by myself to be equal to 0.324. All I really did was I just set the gravitational force along the plane equal to the frictional force and solve for mu, and then I'm going to plug these values in Python to check myself. So here's the Python code running. As you can see right here by the code, the model shown, the object acts at an angle at a pretty constant rate. There's not really much that changes there. It doesn't really go faster. So the result, the coefficient of friction calculated to be 0.324 was correct. The model clarifies this. When the model was run, it actually outputted the same final velocity values as the initial velocity values, meaning that there was no change. There was no acceleration that occurred, so mu was correct. Like I said, Python code matched the calculated values exactly, and velocity was held constant. There was nothing really that changed. So the model held perfectly. Thank you.